Hello and welcome back to the Contaminants Extension webinar series. This is video 2 of 4. Again, my name is Jeffrey McEwen, a project geologist with Sequent out of Denver, Colorado, and I will continue to walk you through the workflow of the Contaminants Extension. So in today's webinar, we are going to discuss domaining. We are going to build two different domains, one through a statistical analysis of our contaminant population in respect to the geological model and water table model that we built in the previous video. We will also build a domain by building a numeric model. So before jumping in, I just wanted to touch on some concepts. Building a proper domain is probably one of the most important initial steps in the contaminant estimation process. For a domain to be valid, it must meet some specific criteria, being the geology within it is consistent, it contains a single contaminant population, and it must show concentration continuity. There's a really important concept called stationarity. Stationarity means that the statistical properties of the data, such as the mean and the variance, do not change throughout the domain. If a domain meets the above criteria, it's likely that the domain will show stationarity. This is important because we want to define a domain and know that it does show stationarity, because this means that any variability that we see in the values is due only to what we are trying to estimate and not other factors. First, let's start with the statistical analysis. Because the contaminant table imported into this project only contains concentration data with no information on geological units or position in respect to the water table, any statistics we view on the table would include data from every unit. While this is valuable, we won't be able to perform unit-specific data interrogation necessary to come up with a statistically backed domain. To do this, we will first need to create a merged table with our geology, water table, and our contaminant data intervals. Because we built our water table from GIS vector data and not borehole intervals, we will need to evaluate the water table onto the borehole traces. To do so, come into the boreholes table, right-click and select New Evaluation. Here you can select any of the geological models of your choice. I'm going to select water table. It will name it accordingly and select OK. I'm going to clear the scene. And this is the object that it just created, a water table evaluation. So all this does is takes, let me clear this out of the way. It will take your borehole traces, and then it will take the geological model, in this instance water table, and then evaluate this model onto your borehole traces to produce this evaluation. Now that we have interval data representative of our water table, our geology, and our contaminant intervals, we can then create a merged table. To do so, I'm going to right-click on my boreholes and select New Merged Table. I'm going to select the contaminant interval, geology, and my water table evaluation, and select OK. And then this will create a new merged table. I'm just going to open it up so that you can see. And now these intervals for the contaminants have the geology and water table information so that we can do this unit-specific data interrogation. Okay, now that we have our merged table, we can run some statistical analysis on it. So I'm going to click this drop down. This is everything that is contained in this table. I'm going to come down to total concentration, right click and select statistics. That will open up this histogram. So contaminant populations can be heavily skewed because of the range of values. As we see, it's from 0 to around 230. So it can be helpful to log transform these values. You do that by ticking on this histogram of the log. And now we can see something that is maybe a little more statistically significant. We can also tick on percentage. So now that the length
And so now the length is represented as a percentage. We also have these values that you can see here, the sample count, the total length, as well as the mean, etc. Another really nice feature of the statistics table is the graph to scene interaction. So if I grab this and pull it down, it will become its own window. I'm also going to really quickly, because all of these samples are so closely spaced and so close to the surface, you can adjust the Z scale axis so that you can get a more exaggeration on the Z scale so that you can evaluate your data better. So it's this bottom right hand corner button, and I'm going to just adjust it to 7 so that we can visualize this a little bit better. Okay, so the graph to scene interaction, all you do is, if you want to see what this value is, you can click on this graph and then it will bring up the values in the scene, which is a nice first pass on evaluating kind of where your higher values are. So if I highlight these high values here, we can see that the high values are relatively spaced out. If they were closer together, we may want to consider subdomaining, but this looks pretty good right now. You can also select other options. So I'm going to toggle on water table. So here we can see that these higher values are located both in the vadose zone and the saturated zone. So we may not want to domain between the two. So I'm going to exit out of this now and look at statistics for the merge table. So again, right click on the merge table and select statistics. There's multiple options. We have a table, we can do scatter plots, QQ plots, box plots, and interval length statistics. I'm going to jump into a box plot. So here you select your numeric column. I'm going to do the total concentration of my contaminant. You can also look at different categories. And then just toggle on these values. I'm going to log transform them so I can get something a little more meaningful. And here we can see that a lot of these higher values are in the outwash and local ice contact deposits as well as the till. You can also apply query filters if you would like. To come back over to merge table, I want to look at some other statistics options. So here we can choose table of statistics, scatter plot, QQ plot, box plot, which is what we just looked at, as well as interval length statistics, which is pretty handy. And when it comes to compositing, so I'm just going to click on table of statistics. So with table of statistics, you have the option of adding a query filter. You can do it length weighted or unweighted. You can add categories. So I'm just going to go ahead and add 2. I'm going to look at my geology table and my water table. You can also toggle on hide empty categories and hide inactive rows to kind of clean it up. I'm going to enlarge this. And I want to look at my total concentration in respect to these units. I'm also going to group by numeric item. So here we can kind of start to see how things are broken down in terms of geologic unit and these unconsolidated sediments as well as the water table. So just looking initially, I can see that the bedrock doesn't really have any samples and the values are relatively low. So I'm going to go ahead and take this. You just click on this drop down to toggle units on or off. I'm just going to go ahead and pull bedrock out because I I don't think I'll be including that in my domain because there's not a statistically significant population and the values are relatively low. So just looking at these initially, these are all unconsolidated sediments. The mean value in the outwash ice contact deposits and the till are pretty similar, meaning that the samples are distributed in similar concentrations across these two units. So usually I would take out the outwash deposits if these were the values, but this is a statistically insignificant number. And considering that this is also an unconsolidated sediment, I don't really see a reason as to why the plume wouldn't migrate into this unit. So at this time, I'm just going to keep all three of these together. A really nice feature of Leapfrog is that it is dynamic, so further down in the estimation process, if I do decide that I want to remove this outwash deposit unit, I can, and then all of the changes will cascade through the project so that I don't have to go back and manually change anything. So leaving something in and changing it later really is not that big of a deal, because as your estimation becomes more fine-tuned, you can come back and change stuff in these initial steps without it being costly in terms of time management. So I think at this point, my domain that I'm going to go with is my unconsolidated sediments domain. So I'm just going to exit out of this. So now that we've decided on a domain let me toggle on these units. So now that we've decided that we're going to domain the plume to the unconsolidated sediments being these three units, we will need to create a domained model under the Geological Models tab. So I'm just going to right-click, select New Geological Model. I'm going to select Geology as my base, set this to 30, and close the extents of my other model because I want these to be consistent. And I'm going to just call this domained model unconsolidated sediments. And select OK. And this will be a relatively easy one to build. So I'm going to go ahead and open lithology. So I want this unit to be split into bedrock, and then I'm going to combine all of these units. So I just need to add a new unit called unconsolidated sediments. Okay. And for the purpose of this model, I'll make this brown and this green. I'll change this one. And then go ahead and click OK. This surface chronology. So I'm just going to create a new deposit. Actually, I'm going to right-click New Deposit from Surface, and then just grab that bedrock surface that I used in my last geological model, and click OK. And we're going to say unconsolidated sediments is younger than bedrock. And then this is the surface that it created. I'm just going to go ahead and activate this surface. Alrighty. And now we have a new domain model where all of our unconsolidated sediments are combined into one unit, which we are going to use as our domain. Something that's also good to do when it comes to when you create domains out of your geologic units is to further domain them through a distance buffer. That way, let me just pull in my boreholes. That way, whenever the estimation process is happening, in areas where there is no drilling, it's not going to interpolate too far beyond this and blow out the estimation value. To do this, we are going to initially need to create a new points object. So I'm going to right-click on points and select new interval midpoints. I'm going to select my geology and click OK. All this is doing is taking all of my geology intervals, taking the midpoint, and creating a point object for each one of those. The reason that I'm doing this is because I am going to create a distance function, and I need something to base the distance function on, and point objects are really, really good for that. So that's this object here. So again, this just created points. To use the points to apply a distance function, come to Boundary, right-click, New Lateral Extent, from Distance to Points. Here you're going to select that point object that you just created. I'm going to bump this up to around 750, it's just user discretion. And when I'm happy with this, I select OK. And that will result in this. I'm just going to go ahead and clear the scene and pull in just my domain or my unconsolidated sediments. So now we can see that this distance function further domained my domain. That way it's not, again, interpolating too far from known values. So with this domain created, I'm just going to clear the scene and jump into the creation of my second domain. I'm just going to collapse my project tree. So this further constrained domain I'm going to create using a numeric model. So I'm just going to throw my contaminant intervals back into the scene so that we can kind of see what we're working with. So immediately looking at these values, you can kind of start to understand the behavior of the plume and the dimensions of the plume. It's helpful if you come over to value filter and kind of filter out some of these lower values so we can get a look at the dimensions of the plume. So here we can already kind of start to imagine what the plume will look like. What I notice initially is that the plume is not isotropic, it's anisotropic. Because of this, we are going to need to find a plane of anisotropy or direction of maximum continuity. It's probably going to be something like this. To do so, I'm going to create a numeric model with an isotropic interpolant to get a non-biased directionality, and then with this directionality I can apply it to a new anisotropic numeric model. To do so, I'm going to right-click on numeric models and select new RBF interpolant. So Leapfrog uses FastRBF for its numeric models, or a radial basis function. This is similar to other Kriging estimators, except that this is not a local estimator, this is a global estimator. You also have the ability to set drift behavior. It's really good for interpolating between sparse, unevenly distributed data. So initially I'm going to want to set my numeric value to the total concentration. You do have options for compositing. In this case, because there is only one sample per borehole, I'm not going to do compositing, so I'm going to leave this as no compositing. We have to set a boundary, so I'm just going to stick with what I've been doing and use the initial extents that I chose. Set the surface resolution to 30. And I'm going to name this interpolant isotropic interpolant and click OK. So with those initial parameters set, I'm going to need to jump into this interpolant and change a few more things. If you click this drop down, you can see that this is composed of a boundary, a trend, the interpolant values, isosurfaces, and output volumes. So I'm going to go ahead and clear the scene and pull in these values. So what this does is it takes the mid-interval point of all of our contaminant intervals and transforms it into a point. And then it uses these points to estimate values in between. So I'm just going to double click on my interpolant. And there's multiple tabs in this interpolant. So it's the boundary, which is what we just set. Compositing, we're not going to do any compositing. I'm not going to transform my values, but you do have the option to log transform the values. Trend. So like I said, this is an isotropic interpolant. So I'm not going to alter any of these ellipsoid ratios because I want it to have equal influence in all directions. And now to the interpolant tab. So there's multiple options in this interpolant tab. I'm just going to start at the top and kind of move around and discuss a few of these. So the interpolant, you can either choose linear or spheroidal. So the linear interpolant assumes that values a certain distance from a point have a proportionally greater influence on that point than values further away. While the spheroidal interpolant works well when there is a finite range beyond which the influence of one point upon another should fall to zero. The linear interpolant is good for geotechnical data as well as modeling geologic units, while the spheroidal is good for contaminant populations. This is also used in the mining industry, so spheroidal is really good for metallic deposits. So I'm going to go ahead and select spheroidal, jumping down to the total sill. So the total sill controls the upper limit of the interpolant function, where there ceases to be any correlation between the value and the distance from the value. So I'm just going to go ahead and set this to 2000 maybe. You can change this around. So the base range is this range right here from 0 to 2000. The base range should be set to 2 to 2.5 times the distance between the boreholes. So I'm just going to move this out of the way. I'm going to set this to a little bit higher so that I can snap to these points and start measuring some of these distances. So that's 825, 434. Again, these are unevenly distributed, so this is kind of discretionary. 796. Alrighty. So anywhere between 500 to 1,000 meters apart. So I'm going to set the base range to maybe 1,800. And now to the drift. The drift controls the way the interpolant decays away from the data. A constant drift means the interpolant will decay to the mean value of the data, while a drift of none means the interpolant will decay to a value of 0 away from the data. In this case, I'm going to go ahead and go with none because I checked earlier and the the mean value of all of these is around 26. So moving away from this sample, I don't want it to decay to a value of 26. I want it to decay to a value of 0, because moving away from these higher concentrations, you will naturally move to a value of 0. And I don't want anything kind of blowing out these values. So I'm going to say drift of none. Moving over to alpha. So this is how steep the interpolant rises towards the total sill. The total sill right now is at 2000, so it'll dictate the steepness of the slope of this line. An alpha of 9 gives the best approximation for spheroidal variograms, but takes longer to process in most situations than a value of 3. I'm just going to go ahead and change it to 9 and just look at the slope. Okay. And nugget. So nugget is variance at close distances. This is used frequently in metallic ore deposits, especially in gold, where there can be pretty high short scale variability. In the contaminant space, this is less applicable, so I'm just going to keep this at 0. And when I'm happy with these, I'm going to jump over to outputs. So the outputs, it automatically creates these ISO values for you. I'm going to change these to something a little more meaningful to our specific data set. So I want something that's a low value, a medium value, and a high value. So in this case, I'm just going to change this to 4. This is all arbitrary, and you can change this later. But yeah, I'm going to change that to 4. 50 will be my medium value, and 100 will be my upper value. And this will create these different intervals. And again, 30. And when I'm happy with this, I'm going to select OK. And now that that's done processing, I can come into this output volumes folder and start dragging some of these in just to kind of see how it's behaving. I'm also going to change this back to 1 just for visualization purposes. I'm going to pull this in. Okay, we're kind of starting to get a shape. We can see that it's subtly dipping. I'm going to pull this in. Alrighty. So from this, we can start to kind of deduce in a non-biased way what the plane of anisotropy is for this specific plume by toggling these on and off, kind of looking at the plume, seeing how it's behaving. So with this, I'm going to drag it to where the plume is kind of flat lying. I'm then going to draw a plane so that I can get a measurement on this plume. So I'm going to come up here to the draw plane line and click that, and then just start drawing some planes. So that looks like it's dipping a little too steeply. So I can redraw the plane, or I can just come over here and adjust it. So that's looking pretty good to me. In my first pass, maybe I'll make it dip a little less, maybe half a step. 70, 250, or 0.5 and 70. So now we're going to want to set the pitch, which will be the direction of maximum continuity. So I just came up and clicked on this plane, and the pitch is represented by this green line right here. So I can see that the plane is, or the plume has continuity in this direction. So let me see. Alrighty. So I think I'm going to do something like this initially. And again, Leapfrog is dynamic, so you can make these determinations and then come back later and modify them. But that looks pretty good in terms of the behavior of my plume. And when I'm happy with that, I'm just going to take these numbers down so that I can apply them to an anisotropic interpolant. So to do so, I'm just going to copy this and select OK. That way I don't have to redo all of the workflow for this. I'm going to double click on my anisotropic interpolant, come to trend, and this is where I can apply this trend. So I'm just going to take these values from my plane, or actually you can actually just select this set from plane button, which will take these values here, and it will automatically create an ellipsoid ratio of 331. So that just means it's stretched more 3 times in this direction, 3 times in this direction than it is in the Z direction. And I can see that there's more continuity in the pitch direction, which is this green arrow. So maybe I'll go ahead and set this to, I don't know, something around 10, 5. That way it stretches more in the direction of the pitch. I also want to come in and adjust my outputs. So we don't need all of these different thresholds. We only used these in the isotropic model to kind of understand the behavior with these low concentration, medium concentration, high concentration populations. For the purpose of creating a domain for the plume, I'm just going to use a threshold of above 4 and below 4. I chose 4 because I looked up the threshold at which chlorine is safe in the environment, and that is at 4 ppm. So anything above 4 ppm will need to be remediated. So for the purposes of the plume, anything above 4 is going to be considered part of the plume, and everything else will just be background values. And when I am happy with all of these parameters, I can go ahead and select OK. Alright, I'm just going to jump into this folder. Oop, not the isotropic, the anisotropic. And let's go ahead and clear the scene. I'm going to pull the values in so we can view them with the output volumes that were created. And here is our plume. So upon immediate inspection, we can see over here that it terminates against the model extents, which is, it's not terrible, so it's not super off in this situation. Something of more concern is how it kind of blows out in this direction over here and ends in a point. So I think I'm going to go in and modify. You can add ISO contours or ISO values, which are essentially just adding sample values for the interpolant to use to further constrain this, because I don't think that it blows out in a point in this direction. I don't really like that shape. To do that, you need to come to your interpolant values, right-click, and select New Contour Polyline. Here it gives you the option to change the value on the contour, so I'm going to change it to 2, just because it's less than 4 and will help domain the plume more. And click OK. And that'll bring up this extra bar right here. So you can either draw 3D lines on objects in the scene. What I like to do though is draw 2D objects on the slicer tool. So I'm going to draw a slice right here because I want to put the point right there. And I'm going to change this to be behind, and then I'm going to come over here. You need to select this to draw the points with the 2 values. You need to select draw points, and I'm just going to put it right there. And when I'm happy, select save, and then that will reprocess this numeric model with that new value. Alrighty. And now that shape is a little better. It's less pointy. I can also maybe put some values to domain it over here. I'm just going to see kind of what's happening over here. So that's a 45 value. Yeah, maybe I'm just going to add something like a point right here. So I'm going to come back to my slicer and just slice right there. New point. Click save. Turn off my slicer. Alright, so that's a pretty good shape. And when I'm happy with this, that is my domain. So I'm going to exit out of my interpolate editing. And that bookends what we are going to discuss today. So just to go back over the topics that we covered. So we created 2 different domains. We created one domain from a statistical analysis and unit-based data interrogation, and came up with the unconsolidated sediments domain. We then created a more constrained domain using the numeric models. We initially got the behavior and direction of maximum continuity through an unbiased isotropic interpolant, fitted a plane to it, and then applied that plane to an anisotropic interpolant, set the threshold at above 4, and created this more constrained domain. So next week we are going to jump into the contaminants extension. We are going to use both domains, the less constrained and more constrained domain, for 2 different estimation processes, and evaluate these onto a block model.